Okay, so yeah, it's my pleasure to be here. And today I'm going to talk about gravitational instantons and harmonic maps in joint work with my former advisor, Song Sun. And there are two things in my title, gravitational instanton and harmonic map. Okay, so I should talk about what are these gravitational instanton and what are the harmonic maps I'm going to talk about in my talk. So by gravitational instantons, in my talk, gravitational instantons are just complete, non-compact Ricci flat metric, Ricci flat four-dimensional manifold. Mg, and with an extra assumption on the regularity. So I'm going to assume the energy is finite in my talk. It's Riemannian manifolds, yes. And so that's going to be my gravitational instant in my talk. All right. And what do I mean by harmonic map? When I talk about harmonic map in my talk, I actually mean axisymmetric harmonic maps. So when I say harmonic map, it always means axisymmetric harmonic maps. Okay. And the domain, I'm going to use phi to denote axisymmetric harmonic map. The domain of my harmonic map will be R3 outside of this z-axis. Okay, so this gamma here is the z-axis of R3. And the target of my harmonic map would be space of positive 2x2 matrices with determinant equals 1. Okay. Positive means that the matrix is positive definite. Symmetric, of course. Yeah. So positive 2x2 matrices with determinant equals 1. That's my target. And it's actually just the hyperbolic space. It's a symmetric space. Okay? This is nothing but the hyperbolic space H2. All right. So the domain will be R3 outside the z-axis. The target will be a hyperbolic space. Okay? And I should draw a picture here. So this is going to be my z-axis inside of R3. So this is my z-axis sitting inside R3. And I also have the word axisymmetric. What does axisymmetric means? So in R3, around this z-axis, you have this rotation here. Okay. By saying that the map is axisymmetric, means that the map is invariant under the rotation. So that's my axisymmetric harmonic map. Fine. On the rotation. Okay. So that's the harmonic maps that I'm going to talk about in my talk, axisymmetric harmonic maps. All right. And because the map is invariant under the rotation, we can also understand the map as a map from the right half plane into the hyperbolic space, okay? From the interior of the right half plane. Okay? So my H here is the right half plane. Okay? The reason is very simple, because my map is invariant under the rotation. You can quotient this rotation, and the rotation, I mean, if you take R3 quotient the rotation, you get the right half plane. So we can also understand the map as a map from the right half plane into the hyperbolic space. Okay? But the key thing is that it's harmonic if you treat this as a map from R3 into the hyperbolic space. It's not going to be a harmonic if you treat this as a map from the right half plane into hyperbolic space. Okay, so this is the harmonic one. Okay, and the gamma, the z-axis will be the boundary of the right half plane. Okay. So gamma is the boundary of the right half plane. All right, so that's gravitational instanton. That's axisymmetric harmonic map. And before I talk about my main theorem, there's another thing I have to talk about. That's the asymptotic geometry. for gravitational instantons. Okay. So what do I mean by asymptotic geometry? It means that we only consider gravitational instantons that are asymptotic to certain model at infinity. Okay? So it's already a problem to show that every gravitational instanton is asymptotic to some model, and it's also a problem to classify all the asymptotic models. But I'm not going to talk about that problem today. I'm just going to tell you some very classical asymptotic models. So there's the ALE gravitational instantons. This basically is just the quotient of the Euclidean space. And there's the so-called ALF gravitational instanton. This ALF model is just a circle vibration over a flat three-dimensional space, and the circle vibration stays constant size at infinity. And there's also the AF beta asymptotic model. Okay? And we are going to talk about this AF beta model in our talk. Okay? And what is this AF beta model? What is this AF beta model? It's basically just the Z quotient of R4. So AF beta model, in my talk, is defined to be a Z quotient of this flat R4. And what is this Z quotient here? This Z action. So Z action here generated by so the Z action acts on R2 cross R1, and the generator of the Z action acts as a rotation on R2 by 2 pi beta and the translation on R1 by 1. Okay? So that is going to be the generator of my Z action. Okay? It's a rotation on the R2 factor and a translation on the R1 factor. It's translation by 1 and rotation by 2 pi beta. Okay? And as you can see very easily, this Z action is an isometric action, and it is a free action, so you can take the quotient. This L, yes, means locally. Like this means asymptotically locally Euclidean, asymptotically locally flat. This is just asymptotically flat. Just terminologies.
Beta is some irrational number.
Beta is some number here, yeah. And yeah, and there's a range for my beta. The range for beta is between 0 and 1. Because if your beta is greater than 1, then you can always minus this thing by 2 pi. So there's a range. Up to isometry, there's a range for beta, 0 and 1.
And choice of gamma here is any like measure 0 step, or it's specifically choose to be the axis or some.
You mean my gamma here?
Yeah.
No, my gamma here is always the z-axis. Yeah, it's very important. Yeah, it's always the z-axis. Because I'm talking about axisymmetric harmonic map, so it's invariant on the rotation. So of course, the set should be the axis. Okay, any more problem?
There are boundary conditions on axis.
Yeah, I'm going to talk about that for harmonic maps. Yeah. Right. So as you can see, this is flat. So of course, it's richly flat, and you can consider gravitational instantons that are asymptotic to this model. Okay? And by AF beta gravitational instanton, it just means this gravitational instanton that is asymptotic to this model at the polynomial rate. Okay? So that's the AF beta asymptotic gravitational instanton. All right. And I have some remark about these models. So if you consider the asymptotic cone for this model, asymptotic cone, then the asymptotic cone is going to be half plane. It's the flat half plane. If your beta is irrational here, and it's going to be a flat cone, flat three-dimensional cone. If your beta is rational. Okay. And one more thing about this AF beta asymptotic model is that it has cubic volume growth. F beta has cubic volume growth. These are just some basic facts about this asymptotic model here. All right. So now with these three things, I can state my main theorem. Erase this part. So what is my main theorem? I'm going to introduce some topological space first. So let x 2k plus 1 to be the four manifolds R2 cross S2, connect some with k CP2 reverse, connect some with k CP2, and x to k to be R2 cross S2, connect some with k plus 1, CP2 reverse, connect some k CP2. Okay. And by CP2 reverse, that just means Euro CP2, but under the opposite orientation. Okay. Connect some k CP2 reverse and k CP2, it's k plus 1 k. These are just some four manifolds. And I can now write down my main theorem. Okay. So John work with my formalizer in 25. It says that for any beta, strictly between 0 and 1. Oh, my k here is non-negative integers. Okay. Got to mention that. And for any number n, any integer n, there exists and AF beta gravitational instanton on Xn. So that's our theorem. It says that for any beta, we have the parameter beta here. So for any beta between 0 and 1, and for any integer n, you always have an AF beta gravitational instanton on Xn. Okay. Basically, just some Ricci-Fab metric. Right, so, yeah, 2 Killing fields, yes. That's why I mentioned. Yeah, exactly. That's what I'm going to talk about. It's a very classical story in the physics world about that thing. Yeah. All right, any question? Mm-hmm.
In Lorentzian signature, this reduction that you're about to present becomes completely integral.
Yes.
Is that the case here too?
Yeah, it's just a Riemannian analog of the thing you just mentioned. Yeah, of the reduction. Okay, so let me give some remark about this before I continue to the proof. So there are some remarks. The first remark is for the people who are familiar with general relativity. So if you are familiar with general relativity, you will know that there's a Kerr black hole, and there's a Riemannian analog of that. That's called the Euclidean Kerr metric. And if you do our construction for n equals 1, if you pick this n to be 1, well, for x1, topology will be R2 cross S2. The construction gives you the Kerr metric. Okay. It's the Riemannian version of the Kerr black hole here. If you do the construction for n equals 1, you get Kerr. Okay. And the second remark, if you do this construction for n equals 2, the topology will be R2 cross S2, connect some with CP2 reverse. Then the construction will give you the so-called Chention metric. The construction. Gives Chention. Okay. I'm not going to explain what is this Chention metric. The Chention metric, I mean, these two people, they are two physicists, and they used integrable system to write down an implicit metric, which is a gravitational instanton on this topology, in 2010, and that's this so-called Chen-Tio metric. I'm not going to write down the formula, but you have an explicit formula for that. The beta here is always between 0 and 1 for this. You mean parameter? The parameter is exactly beta. So in the curve case, it's a little bit different. In the curve case, you can do 0 and 1. Okay. If you pick beta equals 0, then you get a Schwarzschild metric. Yeah.
In the signature, the regularity at the axis sees where the black hole meets the rotation. So is there an analog here too?
You mean regularity problem?
In the signature, there are two very special points.
I know. Yeah. You mean the extreme curve?
No. Regular. On your gamma, there are 2 points that correspond to where the black hole intersects with the axis rotation. And the harmonic map is singular there in a very specific way.
Yes, exactly. Yeah, we call that as turning point. Yes, we also have that in our yeah. But we are going to talk about that later. Yeah.
So what is
so you just basically just replace t by it. Yeah. But you need to make some other change. Like there's a parameter a, you need to replace the sign before a by minus or plus, I think. Yeah. But you have an explicit formula for Riemannian curve as well. It's a metric on R2 cross S2. That's that. All right. So these two remarks. And I have one last remark here. That's for complex geometers in this room. The last remark is for complex geometers. So remark is for Kerr and Chen-Tio, you have the complex geometry. They are conformally scalar. Are conformal to scalar matrix. So for Kerr and Chen-Tio, you have a complex geometry point of view, but the very important point about our construction is if you pick n greater or equal to 3, then there's no complex geometry. That's a very important point. No complex geometry. Construction. Okay. So this conformal scalar things only happens for n equals 1 or 2. That's kind of an important point for our construction. Okay. All right, so today, I think I can erase that. This is the less important page. Today I'll be focusing on running this construction for n equals 2. Okay? N equals 2 means the Chen-Tio case, but the construction for n greater or equal to 3 is basically they share the same idea. So I'll pick the easy case, n equals 2 case, to show you the idea of the construction. Okay. So we'll focus on x2. That's what we are going to do on x2 today. All right. So if you still remember, in my title, I have the gravitational instanton. Also have this axisymmetric harmonic maps, and there's a relation between them. That's why I include them in the title. So there's a relation between torque Ricci-Fine metric, and harmonic map. That's the next thing I'm going to explain. So what's the relation between them? So the setting I'm going to consider is I'm in the local setting. So my MG will be a Ricci-Fine metric with free T2 action, free isometric. Okay. So I'm going to consider a local Ricci-Fine metric that has a free isometric T2 action. And I have an extra assumption here. I'm going to assume this metric to be integrable. So I'm going to assume this to be integrable. And what does this integrable means here? It means that if you look at the distribution orthogonal to the T2 action, this distribution is integrable. So that's what I mean by saying that this Ricci-Flat metric, this toric Ricci-Flat metric is integrable. So basically, you can pick two Kuning fields that generates your T2 action, and at each point you can look at the distribution that is orthogonal to these two Kuning fields, and this integrability assumption means that this distribution is integrable. It's not a very strong assumption because I won't explain here, but in the global setting, if you have a T2 action, isometric T2 action, and if your T2 action has a fixed point, then the metric will be integrable automatically. Not a very strong assumption, actually. Okay, so that's my setting. And to relate such object to harmonic maps, there are 3 steps. Okay. There are 3 steps. Yeah, exactly. No. Bitoric, usually, I mean, for us, bitoric, it just means that you have a isometric T2 action. That's what I mean by toric, but does not include. Yeah, it does not include. It's just some terminology. Okay. Any more questions? Okay. So in the next, I'm going to show how to relate this toric Ricci-Flat metric, integrable toric Ricci-Flat metric to axisymmetric harmonic maps. So there are 3 steps. The first step is you pick 2 Kuning fields, partial phi 1, partial phi 2. You pick 2 Kuning fields, generate this T2 action. Okay. Any 2 Kuning fields works. And you define the matrix Gij to be the product of these 2 Kuning fields. Okay. So I get a 2x2 matrix. It's just the metric on the torus. Okay. And we also define rho to be the square root of the determinant of your G, which is positive. Okay. And I'm also going to denote the quotient of Mg by the T2 action as NH. So basically, I'm doing nothing here. I'm just introducing some notation. Okay. This G will be the metric on the torus. Rho is the determinant, square root of the determinant, and NH is the quotient. Right? Yeah, the second step. The second step is by some computation, you'll realize that the Ricci-Flat assumption on G, the Ricci-Flat assumption on the metric G, implies that the function rho is a function on the surface, implies that the function rho is harmonic on NH. Because this T2 action is an isometric action, so everything is T2 invariant. So your function rho, of course, is a function on the base. And the statement here says that using some calculation, you really realize that the Ricci-Flat assumption implies that your function rho is actually harmonic on the base. Okay? It's a harmonic on the 2-dimensional base. And with this harmonic function, what you can do is you can find, because we are on a 2-dimensional base, what you can do is you can look for the harmonic conjugate of your function rho. So find a harmonic conjugate. V. Okay. You have the harmonic function on the base, and you can look for the conjugate C. And if you put this rho and Z together, then you get an isothermal coordinates for the 2-dimensional base.
No, that's a harmonic conjugate.
Yeah, so if you're not familiar with the notation, so you can do this. You can look for a function dz such that it's closed. Because it's a harmonic function, so of course it's closed. And we are in the local setting, so you can find out the z. That's what the harmonic conjugate. All right, and the point is, if you use 0 and z as the coordinate, then your coordinates are harmonic functions, and your metric will be diagonal under this coordinates. Okay? So the thing is, 0 z isothermal coordinates for h, and you can write h as a diagonal metric under this isothermal coordinate. Okay, and this nu will be some function here. You can write the metric in a diagonal form. That's the point. Okay, and moreover, you can use the coordinates rho and z to identify your n as a sub of the domain of the right half plane. Okay? So for the right half plane, this is my right half plane. We can use rho and z to parameterize the right half plane. So this distance will be rho, and my z here will be parameterizing this z-axis. So with this rho and z, this isothermal coordinates, you can identify your n as a domain instead of the right half plane. Okay? So you can treat n as a domain in the right half plane using these coordinates, rho and z. Okay, and using the integrability assumption, you remember, we assume the metric to be integrable. Integrability will tell you that the four-dimensional metric can be written as the metric on the base plus metric on the fiber. That's where you want to use the integrable assumption. Integrable tells you that the metric can be written as the metric on the base plus the metric on the fiber. Okay? This is the metric on the base, the metric h, and this is the metric on the torus fiber, G. Okay. All right, and our last step. In the last step, you can define phi to be 1 over rho G. This G here is just this matrix. And if you divide this matrix by rho, then the determinant of phi becomes 1 right now. Okay? So in particular, you have determinant of phi is 1. And the map phi will be a map from a domain of the right half plane into the space of positive 2x2 matrices. With determinant equals 1. And that's how you start with a toric-Ricci metric to get to the map phi. Okay. And the final word I want to say here is that maybe let me write over there. Going to erase these settings. Okay. The final thing is being Ricci-fed will be equivalent to this map being X-metric harmonic. And final thing for step 3 is this four-dimensional metric. I'm going to replace G by rho phi. Okay. It's Ricci-fed if and only if phi from the domain of right half plane into the hyperbolic space, where the space of matrices is X-metric harmonic. Okay, and you also have this nu here. The point is, nu will be determined by phi. Okay, nu is determined by ODEs. Okay, the point is, once you know what is phi, then you can solve this ODE to get what is nu. Okay, so the actual important thing here is the map phi. Once you know phi, you know nu. Okay, so that's the final conclusion for step 3, and that's the final. That's the correspondence between toric-Ricci metric, integrable toric-Ricci metric, and axisymmetric harmonic maps. Okay. Patient so far? Okay. All right, so yeah.
So if you have a G, you can get this rho and therefore phi. If you have phi, is rho just some gauge freedom, or is there like some separate data?
No. The thing is, like I said, like this picture here, rho and z, they are actually coordinate functions for the right half plane. Yeah. So once you have phi, remember this map phi is defined on a domain of the right half plane. So once you have phi, you just multiply that by rho, you get Ricci metric. Yes. Rho is a coordinate function. Okay. All right. So now, I guess you can imagine that our construction, it's still over there. Yeah. Our main theorem, our construction of this AF beta gravitational instanton will be constructing some suitable harmonic maps. And that is indeed what we are doing here. We're going to construct this gravitational instanton by constructing suitable harmonic maps. Okay. Next thing I want to talk about is this tameness or harmonic map. Okay. The thing is, the point is, you don't want an arbitrary axisymmetric harmonic map from the right half plane into the hyperbolic space. You want the metric that is associated to this harmonic map to close up to be a metric on the four manifolds. So you need to have some control on the harmonic map. And that's precisely this tameness condition means. Okay? I'm not going to give you a precise definition, but just let me say that conceptually, tamed harmonic maps, it is tamed harmonic maps. Conceptually, it just means that axisymmetric harmonic maps from the right half plane hyperbolic space such that, so for such a axisymmetric harmonic map, from our correspondence, you have the Ricci metric, and tameness means that your Ricci metric, so that such that Ricci metric closes up to four manifold. Okay. So conceptually, tamed harmonic map means that the harmonic map indeed gives you some meaningful geometric object. Okay. It means that the Ricci metric associated to the harmonic map closes up to be a metric on four manifold. Okay. So,
very naive question.
So,
like often these harmonic maps into like these kind of group manifolds
Mhm.
can be interpreted also in terms of gauge theory. It's some like
yes,
like
indeed,
gauge
yes,
bundles
yes.
or something.
I think there are also, yeah,
There are also-
that I don't know. What I know is that for Young Mills, there's also a similar reduction to harmonic maps. Yeah, some kind of Young Mills. Yes, that's the only thing I know. Yeah.
Yeah, absolutely. But I don't know if the team.
I'm going to talk about that very soon. Okay, yeah. Okay. Any more questions?
What's the name that's come from?
So it's a name made up by us. Like we want the harmonic map to have some nice behavior, and we use this word to describe that. Like tame means that the behavior is nice in some sense. Yeah. Okay. All right. So like I said, so right now I won't give you a precise definition, but I will let you see some example first. Let me give you some example of this.
Four dimensions. If you're having a boundary, having an inner boundary where gamma is what you call tameness allows for that.
What I mean by tameness is that the harmonic map has some specific behavior near the boundary, and the behavior is the correct one. Yeah, the gamma is the boundary. And
is that on some portions of gamma just close up. It's like polar vortex.
yeah, and on other part you have black holes. Yeah.
Bound.
Yes.
S2 plus R.
Mhm.
Yours allow.
We don't allow that. We're always close up. Like we don't have this open. Yeah. So in the GR setting, sometimes for curve you draw the picture like this, right? And we don't have this thing. Like it's always this.
Only boundary is the linear.
Yeah. The thing happens at infinity. That's the only boundary in the black hole setting. Yes. All right, so let me continue. Like I said, I will first give you some example of tamed harmonic map to give you a flavor of that. So let's look at some naive examples. Some very naive example. The first, most naive example is that you can consider this harmonic map. It's a diagonal one, rho 1 over rho, from the right half plane into the hyperbolic space or the space of matrices, whatever you want. Okay? This harmonic map. Okay? And what's the geometric meaning of this harmonic map? You can run our correspondence. You can solve the ODE because you can check that this indeed is an axisymmetric harmonic map. Okay, you can check that. And for this harmonic map, you need to solve the ODE first to see what is nu. I'm not going to do that here, but I will just tell you that if you solve the ODE, you will see that nu can be chosen as 0. So I'm going to choose nu as 0 here. So for this harmonic map, so ODE tells you that nu is 0. And the Richie-Fan metric will be, if you pick nu as 0, then it will be d rho squared plus dz squared plus rho phi, which is going to be rho squared 1. Okay? So this is going to be the Richie-Fan metric. And indeed, you can see this is the flat one. Okay? This is the flat metric. Okay? More precisely, you can write the metric as d rho squared plus dz squared plus rho squared d phi 1 squared plus d phi 2 squared. The flat metric. Okay? So for this harmonic map, you actually get the flat metric. R3 plus S1. Okay. And nu determined by ODEs, like what I said here. I didn't show you this part. The thing is, in your
Unless you add extra
of course, I mean, you first after you get this map phi, then you can yeah. More problem. Okay. Maybe let me just say one more word. So nu will be determined by an ODE, and the compatibility condition for this ODE is exactly that phi being harmonic. That's why you can solve the ODE. All right, so let me continue. Get the flat metric on R3 cross S1. What I want to emphasize here is that you have this toric action, and your partial phi 1, this action, will be the rotation on R3, and your partial phi 2 will be the rotation on S1. So that's my first example here. All right, and my second example. You can consider a somehow more complicated harmonic map. And my R here is the distance to the origin in the right half plane. You can check that this is also a harmonic map. And by ODE, you can solve that. You can find out that nu here is actually 1 over 2R. And the Richie-Fan metric you get here is G equals 1 over 2R. Oh, I'm sorry, I forgot the log. It should be log 1 over 2R. Yeah. So the Richie-Fan metric will be d rho squared plus dz squared plus rho multiplied by phi, which is r minus c, r plus c. Okay. The point is, this is also a flat metric. This is the flat metric. After you change the coordinate a little bit, you will see that this is the flat metric on R4. This gives you the flat metric on R2 cross R2. Here. R2 cross R2. And you have two rotations here. Partial phi 1, partial phi 2. Okay. So I have these two examples here. All right, so what's the point for these two examples? The point is that if you want your Ricci-Fab metric, so whenever you have an X metric harmonic map, if you want your Ricci-Fab metric to close up like R3 cross S1, then you want your harmonic map to have this kind of behavior near the axis. Okay? And if you want your Ricci-Fab metric to close up like R2 cross R2, then you should require your harmonic map to have this kind of singular behavior near the axis. Okay? The point is, for this example, maybe let me draw another picture here. So for the rho over rho example, the domain of your harmonic map, this is your domain of your harmonic map. This is the boundary of your domain. The point is that along the entire domain, along the entire boundary, the boundary corresponds to where your partial phi 1 has a fixed point. You see in the matrix at the boundary, rho equals 0, that's where your partial phi 1 vanishes. Okay. Partial phi 1. Okay. And for the other example, you can draw a similar picture. This is the domain. And this is the origin in the right half plane. You can consider similar things. So for the matrix, you can see that the boundary of your right half plane is divided into two parts. So when on the z-axis, when z is positive, your partial phi 1 becomes 0. It has zeros, vanishes. And on the lower part, when z is less than 0, on the z-axis, r plus z equals 0. So that's where your partial phi 2 has the zeros. Okay. That's the picture I'm drawing here. Okay. This is the so-called raw structure in the physics language for these kind of things. Okay. So let me repeat this again. The point is, if you want your Ricci-Fab metric to locally close up like this, like if you want your partial phi 1 to have zeros on the boundary, then this is the behavior you should impose on the harmonic map. Okay. And if you want your Ricci-Fab metric to close it up like this, like you have two Killing fields, two rotation Killing fields, and they both have zeros, and at the origin, both of them vanishes, then this is the behavior you should impose on the harmonic map. And the general philosophy here is that if you mix this kind of behavior up, then you can create a much more complicated topology. For this example, the topology is still very simple. It's R3 cross S1. For this example, the topology is R2 cross R2. But if you mix this kind of behavior up, you can make much more complicated topology. Okay, then that's how we get the topology of X2. All right. So all right, so get back to the construction of X2. Let me remind you, X2 is R2 cross S2, connect some with repeated reverse. Okay, so if your X metric harmonic map has this kind of behavior, you get a metric on this. If your X metric harmonic map has this behavior, you get a metric on R2 cross R2. Then the question here is, what kind of asymptotic behavior you should require on your X metric harmonic map to get a metric on this guy? Okay, that's the problem here. And the answer is, if you like, this is the domain of my graph, it's the domain of my X metric harmonic map. The answer is if you divide the boundary into 4 parts, this part I've labeled this as partial phi 1, this part as partial phi 2, this part as partial phi 1 minus partial phi 2, this part as partial phi 2. And what's the meaning of this picture here? It means that I want my harmonic map, this part, I want my harmonic map to look like rho over 1 over rho. Okay. I want partial phi 1 to vanish for the metric. I want partial phi 1 to have zeros here. And that's why I need my harmonic map to behave like this. Near this orange part. Okay. And near this part, because I want my partial phi 2 to vanish. If you want partial phi 1 vanish, then you use this behavior. And if you instead want partial phi 2 to vanish, then you just swap this rho 1 over rho. Okay. So you want your harmonic map to behave like 1 over rho. Okay. And similarly has another model harmonic map here. Have another model harmonic map here. You can write down the model explicitly. You just apply some linear transformation to this matrix. You can write down the model here and here. I'm sorry, it's partial phi 1. We also have the model rho. Okay. And for each turning points, you should use the second model here, because this is the harmonic map where you have a turning point. It jumps from partial phi 1 to partial phi 2. So at this turning points, you would wish your harmonic map to behave like this. So at this blue region, you will use some model similar to this. Okay. And finally, because you want to construct an AF beta gravitational instanton, you will also want to improve some asymptotic behavior on your axisymmetric harmonic map at infinity. And so there's also another model here. That's the so-called phi AF beta model. So if you still remember, we have this AF beta flat metric, and you can write down the harmonic map corresponding to that flat metric, and that's the harmonic map here. Okay. We have the AF beta flat metric, and it is associated with the harmonic map. If you still remember the reduction here, and that's the harmonic map here. Okay. So the upshot is, I want to have a harmonic map phi, which looks like rho over rho 1 over rho at this region, looks like 1 over rho at this region, looks like some other model at this region, and looks like rho 1 over rho at this region. And at this blue regions, I want my harmonic map to look like this model. And at infinity, I want my harmonic map to be like this model. Okay. If you have this kind of harmonic map, then the reduction, if you run a reduction, the Ricci-fied metric will be a metric on this guy. That's the point. Okay. That's the point. Okay. So I will briefly mention, like we have already determined what kind of harmonic map we want here, and you still need to show that you can indeed find this kind of harmonic map. So that's the existence and the uniqueness result I'm going to mention. Oh, I forgot. I can give a precise definition of the tame harmonic map now. Precise definition. It means that your axisymmetric harmonic map phi from the right half plane into the hyperbolic space such that the hyperbolic distance, because the target is a hyperbolic space, so you can talk about the hyperbolic distance in the hyperbolic space by model less than c. And distance F beta going to 0 at infinity. Okay, so that's the precise definition of tameness for harmonic maps. Okay. It basically means that your harmonic map here it's very close to this kind of models near this z-axis, and it's decreased. It's going to it is asymptotic to your AF beta model at infinity. That's what this Tamenis condition here means. Okay? You want this Tamenis condition because this Tamenis condition guarantees that the Ricci-Fab metric associated with this kind of harmonic map becomes a metric on this manifold. That's why you want this Tamenis condition. Okay. Questions so far? Okay. These are just the behaviors to ensure your metric close up to be a metric on this guy. Okay. So let me briefly mention the existence of such harmonic maps. So this is the existence and uniqueness. I won't mention the proof because this is kind of the classical part. It's already done by Weinstein and Yan Li and Gang Tian in the Lorentz setting, and in the Riemannian setting, it's basically the same. So it states that this kind of, given this structure, there exists, it states that there exists unique harmonic map that is tamed. Okay. So when you write down this kind of structure, like you specify, like you want this part to be partial phi 1, you want this part to be partial phi 2, you want this part to be partial phi 1 minus partial phi 2, you want this part to be partial phi 1. When you specify this, then there will be a unique axiometric harmonic map that is tamed in this sense. Right? Yeah, that's Lorentzian. But the setting is similar. I mean, in the Lorentz setting, after you do the reduction, you also get this kind of harmonic map. It's just the difference between Lorentz setting and Riemannian setting is that the reduction is different, but you always end with the same equation, always the same harmonic map. Yeah, the bounding condition will be very different. I'm saying that their method also works here. Yeah. So it's a very simple actually. This because you're solving for harmonic map into a negative curved space. You just solve the Dirichlet boundary value problem and do unsolved and you get this. Very simple. Okay? Existence and uniqueness, and you also have regularity. This part is essentially by Li and Tian, and his student. They are the student of Yan and Li, the Nguyen. And you need a little bit more elliptic regularity for the Ricci-Fab metric here, but the conclusion is that the tame harmonic map, you have the unique tame harmonic map here. Gives a Ricci-Fab metric with conical singularity. X2. But the metric is smooth at infinity. Okay. The cone angles are along 2 S2s. Okay. I don't have much time, so I won't explain this in very much detail. I'll just tell you that the regularity theorem tells you that whenever you have this kind of tamed harmonic map, you can consider the Ricci-Fab metric. Then the Ricci-Fab metric will be a smooth metric, but have some conical singularities. And where are those conical singularities? So in my picture here, each finite segment here will be an S2 instead of your manifold X2. Okay? You only have 2 finite segments. So you have 2 S2 here. two S2 here sitting inside this manifold. They are actually the zero set of partial phi 2 and partial phi 1 minus partial phi 2. Okay? They are the fixed point set of these two vector fields, of these two Kinning fields. They are two totally geodesic S2 sitting inside of your X2. Okay? And the theorem says that if you get the Ricci-File metric, then the Ricci-File metric will be smooth everywhere except along this 2S2. Along this 2S2, you might have some cone angles. Okay? So the singularity is very mild. It's only like it's a singular metric only because the cone angle is not 2 pi. That's the theorem, the regularity theorem tells you. Okay? So you have some cone angle. That's the singularity. Okay. All right. So that's the regularity and.
So in your construction, there is a limit boundary. There are these S2. You said that totally.
The totally geodesic, but we usually don't call that as a boundary because it's just a totally geodesic submanifold, subsurface sitting inside your manifold. It's not a boundary. So you are no. In our setting, we are considering 4 manifolds, and you have some Kinning fields. This inner boundary, according to your definition, they're just the zero set of the Kinning fields. There are just some surfaces sitting inside your manifold.
What is the coordinate?
It's coordination 2.
Okay. Then what?
Okay. I roll S2 here, so of course coordination.
Torus action, open part of the torus action extends to some, because it's only free.
And by the way, away from those two, what's the coordination of the rest of the set? Away from these that you can do?
So the picture I draw here is it means that you have a smooth vibration, T2 vibration, except this z-axis, and on this z-axis, this partial phi 1, partial phi 2, they give you the direction of the torus action that has zeros. Like, yeah.
Yeah, of course. S2.
Yes. Yeah.
Away from the S2, still on gamma, but not on the zero line.
That's still coordination 2.
Okay.
Yeah. Yeah, like this part will be a parabola, it's not close. Yeah.
So is there some way to like read off the holonomy from the local models or something?
I can get to that after I finish this talk. Yes. Yeah. That's another part of our paper actually. Yeah, but I don't have much time, so I need to explain a conceptual proof for our theorem. Like I said, you have these cone angles. You don't know this cone angles is 2 pi or not. That's the main problem. And how we solve this problem? I only have 3 minutes, I think, so I'll be very fast.
Angles are following. So the cone angles are where you rotate around.
Yeah.
That angle should have been 2 pi if it was smooth, but it's not.
Yeah, that's the point. Yeah, exactly. Yeah.
And it's only on the yellow.
Yeah, it's only along these two S2s in this situation.
They join up at one point.
Yeah, at this point, the model will be
And those two angles are not the same.
not the same. Yeah, so you can think of R2 theta cross another, like R2 alpha cross R2 beta. You can think of this kind of situation. And by R2 alpha, I mean it's a flat R2, but you have some cone angle version. So that's what's happening at this turning point. Anything. Positive thing, of course. Yeah.
Any alpha, any beta, you can do it.
No, it's just we don't know what's alpha and beta. That's a problem. Yeah.
Okay, so it's the opposite. It's forced by the problem. You don't get to prescribe it at all.
Yeah, we don't get prescribed at all. Yeah, because it's so easy for you to get the harmonic map. You have no information about this harmonic map. It's very easy to construct harmonic map, so you don't have much information about it.
There's also unique. So alpha and beta exist, and that's it, and you have no.
Yeah, you have no idea what's that. That's the problem. You want this to be 2 pi, but you don't know what's that. Okay? Yeah. So let me very fast. The problem is there is no explicit knowledge of these two angles. I'm going to denote these two angles as theta 1, theta 2. Like you don't have an explicit formula. You never know when it is 2 pi, when it is not 2 pi. That's a problem. And the way we solve this problem is, so when you draw this picture, you actually have 2 parameters. The 2 parameters are the length of these 2 parts. Okay. Let me erase those 2 as well. Okay. The way we solve the problem is you have this L1 and L2. Like when you write down this picture, you can specify on which segment is partial phi 2 and on which segment is partial phi 1 minus partial phi 2. So you have two parameters here. Okay? What we did here is that we consider this so-called angle map. So whenever you have an L1, L2, you get a structure like this, and you can solve to get the harmonic map, and you can get the cone angle. So we have this so-called angle map here. What we did is we proved this to be a continuous map. And the key point is, although we don't have an explicit knowledge about these two angles, but we do have some we can understand the behavior. Understand that was that two. When L1, L2 becomes very degenerate. Very degenerate. Okay, and what do I mean by degenerate? Degenerate means that, so what do I mean? I can consider the cube epsilon n sitting inside of this R2 plus. And my epsilon here is a very small number, my n here is a very large number. And the picture I should draw here is so this is L1, L2. So you have a cube here. The boundary of the cube is where degeneration happens. It means that either one of your L1, L2 is very small, or one of your L1, L2 is very large. So you can imagine this picture here will be very degenerate. Either it's very small, or some L2 is very large. So that's the degenerate situation. What we can do is that we proved the image of this degenerate boundary, this boundary of the cube. We can prove that the image of that is something contain the point 2 pi inside. Okay. That's what we did. And this requires a very delicate analysis on the bubbling of the harmonic map. You can imagine that when degeneration happens, you can scale up or scale down, and you can obtain a limit harmonic map. And from this limit harmonic map, you can get the angle information in this limit process. And we can show that the point 2 pi is sitting inside, and by a topological argument, you'll see that there's a point that is mapped to 2 pi. So that's how we finish the function. Okay, I'll stop here.